So now it's time to kick off the primer to the roads to removal, the report highlights. And as we mentioned before, this is a multi-year effort by several leading academic institutions to help the nation understand the potential of CDR removal. There's some impressive findings, and to help us frame that up is Dr. Jennifer Pettridge, the lead author of the report from Lawrence Livermore National Lab. As at earlier discussions meeting today, she also is a leading expert in feline behavioral sciences with a specific focus on a certain species called academic research authors. Come on, we got to get something going here, but no, you see, that's good. For those of you not familiar with the lab, it's one of 17 Department of Energy facilities in the United States. Since 1952, the lab has been instrumental and at the forefront of some of the most significant applied science and engineering achievements of our time, including the December 2022 demonstration of fusion ignition in a laboratory setting. This is like the Oscars. At the National Ignition Facility, the lab's broad focus, 8,000 employees, by the way, is on multidisciplinary research and science for the betterment of society. And climate resilience carbon management is one of those important areas. Dr. Pettridge leads the carbon initiatives at Livermore, serving as a senior staff scientist, a distinguished member of the technical staff, and is a microbiologist by training, well-versed in soil ecology. We love dirt, so thank you. She also leads multiple team projects for the Department of Energy, is a recipient of numerous national and international awards, and has become a co-author of more than 150 peer-reviewed technical publications, collectively resulting in more than 10,000 citations. Oh my gosh, impressive. No, she grew up not far from here, living in both Ohio and Pennsylvania, spending time in Michigan, and a family farm in Nebraska. But we welcome you back to Indiana, so thank you. Yes, we have some special guests. I want to thank both of them for coming. First, State Representative Carrie Hamilton, who, please stand, also joining us tomorrow on the panel. And a special host. I know, Sean, as Dean, you welcomed us, but our real host, the inaugural Chancellor of Indiana University, Indianapolis, Dr. Latha Ramshad. Please, thank you for hosting us. So now, Dr. Pettridge, please.
Thank you all for being here. Thank you, Chancellor. I know you need to go, but appreciate you stopping by. And thank you, Janet, for those wonderful words. It was, it's a hard act to follow. And it's a tough week to be here. You've had a lot going on in the last couple of weeks, right? Future Farmers America, we're just here, and Taylor Swift is coming Friday. I'm so glad you made time to be here for this important topic. I want to represent all of my team here, are just thrilled to not just share the knowledge that's in this report, but we want to hear back from you. We want to really figure out ways to put this work into action. So that's what this is here for. It's here for the panel conversations and those individual one-on-one conversations. So grab us and have that chat about how do I make action happen? And how do I make, there we go. The projector work. All right. Well, I want to again announce that this is a kind of an overview of the report. We have 68 authors on this report. I want to give them full credit, even though not every single name is mentioned here. Without them, we really couldn't have put together such an incredibly interdisciplinary synthesis that we're going to talk about in the next couple days. But before I get into those details, I want to share something that has been incredibly impactful and meaningful to me, and that's a little video that we're going to watch now.
As a scientist, I know by the time she takes her first breath, 9 billion more tons of carbon pollution will be in the air. When she takes her first steps, wildfires will have burned millions more acres she could have explored. The day she gets her first pet, there are thousands of newly extinct species she'll never meet. The night she forgets to call, the night of her first heartbreak. Her future home floods for the first of many times. By the time a child born today goes to college, it may be too late to leave them the world we promised. Our window to act on climate change is like watching them grow up. We blink and we miss it.
That's tough to watch for me every time I watch it. It's probably tough for you as well. But I just dropped off a child, a daughter, at college, and I have a grandson who just turned 1. And it really hits home where we are. Our climate is changing. Our weather is changing. Our energy opportunities are changing. And for all of those reasons and many more, we wrote this report. So I'm going to start with showing you why do we need carbon dioxide removal. But I also want you to think about all of those other reasons, ranging from our jobs, our children, our climate, our homes, the landscapes that we grew up in and that we hold dear. So we have a CO2 problem, and I think we've heard that very clearly from Administrator McCabe, that we've got more in the atmosphere than we know what to do with, and decarbonizing, or the process of reducing our emissions of greenhouse gases, the methane, the CO2, the nitrous oxide, that's something we're well on our way to, and I'm thrilled to hear again how much our government is currently investing in that. But we've gotten ourselves to a position where it's not enough. Even if we were to do everything possible to get rid of the greenhouse gases in our atmosphere, to decarbonize our energy centers and our agricultural structures, it wouldn't be enough. So carbon dioxide removal is, sometimes I call it the last 10%. It's the little bit of cleanup that we need to do for all of those legacy emissions, and also all of those industries like agriculture where we just don't know how to stop. We can't grow crops without fertilizer at the rate that we need to grow them to feed our country. And we don't have a way to reduce the nitrous oxide emissions to the extent to zero. That's just a reality. The same is true for the cement industry, for steel, for many industries. So we have to essentially make up for that with carbon dioxide removal if we want to hold our planet in a place that's going to be livable. It's that simple. And that's what hundreds and hundreds of scientists that are part of the IPCC, or the International Panel on Climate Change, are telling us. Now, the United States is clearly not responsible for the whole thing. That's something like 10 billion tons of removals per year by the time we get to 2050. But what we're responsible for is something on the order of 1 billion tons of removals, and that's what the Biden administration established a few years back. So that's the goal that we set out to essentially assess, can we make it? That's what the science and the policymakers have decided is the right number, but do we have the resources? And what's it going to cost? Is anyone going to benefit? How is it going to affect local communities, their air, their water, and the concerns that they have about jobs? So let me give you a little backstory on how do we get this idea that we needed such a report. And it actually came from a similar analysis that we had done for the state of California, which some years ago decided, we're going to be net zero by 2045. And that's all well and good for the governor to say. That was a big press conference. But then our team, many years ago now, started to think about what would it actually take to hit that target, both in dollars, in biomass, in geologic storage, all the different parts of the puzzle that you need to put together to remove that much CO2 from the atmosphere. So we wrote an analysis that was called Getting to Neutral, and we showed, it's actually pretty doable for the state of California, given the resources that the state has. More recently, talking to folks in the Department of Energy, we thought, if we can do it for the state, let's do it for the whole country. It'll be easy. no, we didn't say it would be easy. We knew it would be hard. There are over 3,000 counties in the United States, and we decided we needed to collect the data for every single one, not just at state level, because each individual county has different resources and different motivations. And we felt the data needed to be collected with that level of resolution, because it's often individual county land managers who make the kinds of decisions which trickle up into policy. So that's a high resolution bottom-up analysis is what we call that. Again, we had multiple different organizations, many different universities, some, yes, Jerome here from Indiana, and all across the United States. So we have representatives here from our team at Livermore, as well as from down in Texas, but we had other national labs. We've really tried to pull in as much expertise as we could. Several different offices within the Department of Energy helped fund this, and they're offices that are really interested in carbon management. We tried to include analyses that went beyond anything anyone else had ever done. Is the land available? Is there water available? Is there renewable energy available? Because we don't want to steal from our existing electric grid, which is already strained by other factors. Is there a workforce available with the right technical skills, and who benefits? So including environmental and energy equity justice was a really novel part of the analysis. At the end of the day, we made a rule for ourselves that we weren't going to write a policy document. We weren't going to wag our fingers and say, you should do this. We wanted to be as dispassionate as one can be in the climate field, which is hard, but to say, here's the data, here's what efficiency and economics tells us makes sense. Feel free to ignore it and go ahead and choose the more expensive option. If that makes sense for your community, that is okay. But here are the opportunities, and here's what would be efficient in the long run. That data, I want to just mention, I don't even know how many data points it is, millions, is all available, I'll just note, at roads2removal.org. That's the website you see right there. If you've got anything on the table in front of you, I'm sure you're going to be able to find that website there as well. It's got lots of short videos if you want to show this to somebody who's a non-expert. It's got a fun little scroller where you can hover over the county maybe that you were born in or grew up in, and you can see what the opportunities are in that individual county. Lots of really fun resources, and I want to thank the Livermore Lab Foundation for helping support that website and for us all being here today. So let me just give you a little bit more detail about what we mean when we say carbon dioxide removal, because it's not just one thing. It's a whole package of techniques. And I should pause here and say these were techniques that we summarized as of now 3 years ago. This was the state of the art where we had enough data at that point. It's already out of date because our technology is moving so quickly. There are new approaches, including, somebody mentioned marine carbon dioxide removal, which are being studied right now, and we are becoming comfortable with applying. In the ag sector, it might be adding crushed rock or enhanced rock weathering. And there are many, many other new technologies coming online every day. But what we analyzed here, again, is what we felt comfortable and what was mature as of 3 years ago. So we start with CO2 in the atmosphere. And I like to make the joke that plants, trees, are the OG of carbon dioxide removal because they do it for free, and it's called photosynthesis, right? That's the way plants work. It's how they get their carbon. That carbon gets stored in the bole of a tree, and in our crop plants, it actually gets stored in the longer term below ground where we can't see it so well. Particularly if those crop plants are perennials and they have real deep root systems that go down and down looking for water, and if those roots exist year on year on year as they do in perennials, they tend to allow carbon to accumulate. I won't go into all the details, but that's what my research has been on for 20 years, and I'm happy to get into it after we finish my talk here. But that carbon can stick around. whether it's in the bole of a tree for 20 to upwards of 100 years, and also as soil carbon. That said, it can also be lost. We've lost 500 billion tons of carbon from the soils in our agricultural landscapes. That's an enormous number. A lot of it as CO2. In the United States, a lot of it literally washed down the Mississippi. Particularly from the Corn Belt, we have simply lost that much topsoil. Every farmer I've ever met out here in the Midwest does not want to lose their soil. That is their resource. And so that is something that a lot of our analyses focused on. So those are the two major, what we call nature or ecological storage solutions for carbon removal. But as you probably know, a lot of our agricultural landscapes, as well as municipal folks, produce a lot of biomass, this waste debris that naturally just decomposes. It might be corn stover. It might be what you put in your green bin if you live in an urban environment and they're collecting those residues that you get from your grass clippings or even from what you haven't eaten at your dinner. All of that biomass put together, if it's taken to a facility that can convert it, can be used to both remove CO2 from the atmosphere, that carbon that was fixed when it was a plant, but also produce really useful products. And I'll go into that more in a moment, but we're going to call that biomass carbon removal and storage, or the acronym we use is BiCRS. Once that carbon is caught from that process, we can store it very durably deep within the surface of the earth, a mile down, in geologic reservoirs that, again, I'll talk more about in a minute. Now, the last way, whoops, I hit the wrong button. Let's see if I can get out of that. The last way to remove CO2 from the air is to literally just suck it out with giant fans, and that's direct air capture. And the government has been investing an enormous amount, this is a relatively new technology, to figure out how we can do that and make it affordable. Because right now it is very, very expensive. But taking CO2 out of the atmosphere that's at atmospheric concentrations, concentrating it, and then again, injecting that deep within the earth or using it to make cement or other products is the last solution that we have in our repertoire of carbon dioxide removal approaches. So I want to quickly get to the solution and not leave you hanging. Yes, we can hit the target that our government established as our goal. We can hit 1 billion tons of removals by the year 2050. We have the resources, we have enough biomass. We're really lucky. Many countries in the world don't produce as much biomass as we do, just through agriculture, forestry, municipal sources. But it's going to cost $129 billion a year. And I like to look people in the eye and see if they flinch when they hear that number, because it's a big number. We're talking about waste management of invisible garbage, right? Who wants to pay for that? Well, let me put it in a little bit of context. We're already paying something like 5% of our GDP in the air pollution that often is caused through our use of fossil energy and the downstream effects on our health. We're paying $93 billion a year these days to just mop up from the various disasters. Helene and Milton, we don't even know the numbers yet, but it will be substantially more this past year. So we are already paying for the costs of our climate and our weather changing. We see an upside with a lot of the opportunity in the carbon dioxide removal space because we've calculated upwards of 440,000 new jobs. And these are often in localities which are losing jobs right now because of the phase out of the older fossil fuels, for example, coal. And so often in those communities where we're talking about capturing CO2 and managing it by injecting it deep within the earth, those are communities that know how to drill a hole in the ground that's a mile deep. Those are communities that know how to manage the long-term testing and verification that that's being done safely. So there are opportunities in this space that are that go beyond our current energy infrastructure. There are also opportunities in our agricultural landscapes where these management of soils in new ways will actually create new jobs. But I want to get back to this idea that later is too late, like we heard about in the video. What you're looking at here, and I'll ask you to just maybe focus on the plot on the left-hand side, is the amount of carbon dioxide removal that we can do in millions of tons per year, and then starting essentially today, this year, through 2050. And what you can see colored by the different four colors are these different overall classes of removal. And soils and forest management both have relatively low per year rates of carbon dioxide removal. So you might say, oh, well, let's discount that. Let's get to the big stuff first. But the reality is we can't, because there's so much capital investment that need to happen. We need new regulation. We need new policy. We need Class 6 permits to be able to inject CO2 down into the earth. And that doesn't happen on a dime. But literally today, yesterday, we've known how to do cover cropping. We've known how to improve forest management so those forests are less likely to burn or be affected by bark beetles, or as Dr. McCabe talked about, planting trees. And that is something that we can do today. So if we start doing some of these near-term, low-hanging fruit approaches, they add up. The cumulative effect, which is what you look on the right-hand graph, the cumulative effect of planting those trees today really brings us big gains in the long term. So I want to really advocate for an all of the above approach, and there's certain things that we need to take advantage of today while we're bringing on board some of the more technological solutions. This is a McKinsey diagram. It's pretty nerdy. It's in the weeds, but I think it's important as it shows you really there's a difference in the cost per type of carbon dioxide removal. So along the bottom axis there, what we're doing is scaling all the way to that billion tons that we want to eventually remove. And then on the vertical axis, what we're looking at is dollars. What does it cost? And if it's negative, that's in the little bit of green there, you show we can actually make money by planting high rotation forests. Now that's not necessarily here in Indiana, but it's definitely true in some of the southeastern parts of the US. At very, very low cost, we can remove carbon in our agricultural soils. It's under $50 a ton. Then as we move into that big set of purple bars there, those are all different approaches to use BiCRS, the biomass carbon removal and storage. And depending on whether we're gasifying to hydrogen or making sustainable airline fuel, the price point is slightly different. But the major take home of this graph is that a lot of the CDR that we need to achieve by 2050 is possible by using biomass. And finally, in the blue, direct air capture and storage, we sometimes call it DACS for short. That's that using the fans to literally suck CO2 from the atmosphere. That's the last resort, really. It's the most expensive thing. It's upwards of $200 a ton. Right now, it's even more than that. We think that by 2050, those numbers will come down. We have an enormous potential to do direct air capture and storage, but it doesn't make sense in every place. It really only makes a lot of sense if you're right near a geologic storage reservoir, which not everyone is, and also if you have access to renewable energy. Again, not every part of the country has that. So let me start walking you through some of these individual topics and giving you a little bit more specific information for the state of Indiana. So I want to start with agricultural systems. I know that's going to be of interest to many of you, both the opportunity space and the potential risks of managing our agricultural soils in terms of climate. So we looked at parts of the country that were growing the top 6 commodity crops. And that's actually why in this particular graph, when we look at the opportunities, California has very little. I come from a state that's a big ag state, but we grow 100 different crops. And so none of the big ones are on there. But Indiana is home to the big commodity crops, as you well know. And so what this figure here is showing is the height of the bar reflects the opportunity to remove carbon dioxide removal through three main pathways. And the first one is cover cropping. The second in yellow is perennial carbon crops. Those are crops like miscanthus or switchgrass, some of the crops that we might grow on our more marginal lands where we're simply trying to produce biomass that then gets converted to something like sustainable airline fuel or hydrogen. And then finally, perennial field borders. It's funny, back when we had the Dust Bowl, this was all the rage, right? We were all putting in hedgerows and areas around the outsides of our fields to hold the soil. And there's some parts of the country that are still really keen on that. And it might seem like a small amount of land, but when you add it up, the amount of carbon that can be stored just through those borders is significant. Across the entire country, we have the opportunity in soils to remove something like 130 million tons of CO2 at a price point of $40 per ton. Now, why am I bringing in the cost there? Well, because the farmer's got to get paid, right? You don't just start cover cropping because it costs you money to put in that extra crop without there being a benefit. And I'll be honest with you, that is a system that we do not have in place in every part of the country. I know in Maryland, there's actually a benefit to the farmer that's paid. And we've got something like 87% of the land there that's in cover cropping. But nationally, it's only 5%. And I've talked to multiple farmers about why they do and don't cover crop. And it's because it's harder than it sounds. It's getting the timing right and the personnel and all of those details, it's not that easy. But if there were an incentive, maybe it would be a little easier. It would be more amenable to a grower to make that happen. Same goes for these perennial approaches as well. So the price point matters. When we looked at a higher price point, if a farmer was paid $100 a ton, we're up close to almost 1 billion tons of removals by 2050. So that's an important thing to take on board. The lower Great Lakes region, particularly Indiana, has some of the highest potential for carbon dioxide removal in soils. It's probably the biggest opportunity. If you were to ask me, what's the one thing I would invest in if I had to choose one, that's the big opportunity here in Indiana. And we looked at that, again, through these three major approaches, but we can hear more from that in the panel this afternoon when both Jerome and Allegra will tell you more about that. Forestry is also a big topic and a big opportunity here in Indiana. Much of the state was originally forested. Across the nation, we looked at moving forests and thinning forests to make them less risky for fire outbreaks, which is important for me out in the western US. Doing high rotation forests, like I mentioned in the southeast, where you essentially treat your trees like a crop. But here in Indiana, it's likely just managing the existing forests to make them less susceptible to disease outbreaks, but also replanting. And the calculations that we did not do, but we've taken from other colleagues, so that there's something upwards of 2.5 million acres where we could be restoring forests, and that results in something over 9 million tons of carbon dioxide that's removed. And you might say, yeah, trees don't live forever. And you're absolutely right. But I think that Janet made a lot of great arguments for why growing those trees helps us in the near term. And for the same reason, more carbon in our soils helps us in the near term keep carbon dioxide out of the atmosphere, prevent some of those climate change effects as we walk towards the bridge, as it were, to the more technological approaches. So let me get into those. If we think about a forest and the carbon that's in the trees, if we burned that carbon, we make a certain number of electrons. But the value of those tree stems, of that biomass, is much, much higher if we think about the carbon that's embodied in that material. It's much greater than the energy value. And that's absolutely true across the state of Indiana, where there are millions and millions of tons of biomass, most of it on agricultural landscapes, a lot of it in corn and soy rotation. And using that biomass, Indiana could capture something on the order of 23 million tons of CO2 per year. Essentially, what we're doing here is just simply not allowing that biomass to decay on the surface of the soil where it just ends up back in the atmosphere, but collecting it and transporting it. Transporting it to a facility where we would then both convert it to a useful product that could be bio-oil, that could be hydrogen, it could be sustainable airline fuel, it could be asphalt. We looked at many, many different techniques. And also capturing CO2 at the same time. There's an opportunity across the whole country to achieve something like 700 to 900 million tons of removals simply through this approach, which again we call BiCRS. It would take a lot of new facilities, something on the order of 300 gasification or pyrolysis facilities across the country. Those are the locations of where we think they would want to be, both based on where the biomass exists, but also where geologic storage exists to put that CO2. That's going to take a lot of investment, and we recognize that. There are a few of these facilities that already exist in this country, but we need more, and we need to figure out how to build them efficiently and faster for less cost. I'll finally here talk about direct air capture. Again, this is the removal of CO2 from the atmosphere and using machines that literally suck it in and run the air over a solvent or sorbent chemical that actually absorbs it, and then using renewable energy to desorb that then concentrated CO2. There are multiple pilot facilities all across the country and across the world, really, that are already doing this. Are they doing it at scale? No. They're doing 100, thousands of tons, and we need to get to millions. That's going to take us time to figure out. But again, this is a place where the federal government is putting significant investment. So thinking of new ways we can use that CO2 that's captured and co-localize renewable energy with these facilities, those are real opportunities as we go forward. Right now, we've got a facility that's out in California near where I happen to live. They're putting that CO2 into cement. And apparently, you can walk across a sidewalk in San Jose that's from CO2 captured from the atmosphere. That's pretty cool. And that's important in the short term because we don't yet have a wide-scale ability to inject it deep in the earth. But let me talk briefly about that. That's the long-term goal that we're hoping for a lot of the CO2 in the atmosphere. Putting carbon back in the ground, to be honest, where it came from. And this is a map of the United States where all of the green areas are really thumbs up, very, very good for geologic storage. And Sue Havorka is here, and she helped make this map with her team. She can tell you all about what's good, what the limitations are. And we'll be talking more about that tomorrow. We know that there are places in the United States that are in the yellow where we might have the opportunity based on the geology, but we don't have a lot of test wells that have been drilled. But Indiana is really sitting pretty in terms of geologic storage. A huge opportunity in this state for doing geologic storage in almost every single county. And at a very, very low price point, less than $10 a ton. Now, we recognize that there are already some test wells near here in the Decatur region that have had some leakage, and we're going to talk about that tomorrow, because this is a topic that is incredibly important to many, many communities, and conveying the science and the length of study and effort that has been put into this space is something that we really think is important to have a conversation about, so that we will have a whole panel on tomorrow. I want to wrap up here by talking about our environmental justice analysis. We felt it was important to not just look at where we had the potential in terms of land or biomass, but what are the benefits, the upsides, and possibly downsides of implementing these totally new kinds of industries. So there are risks and there are benefits. And Kim Mayfield, who's also here and will be talking and leading a panel shortly, will serve as a resource for the 27 different approaches that they looked at. And they range from the social vulnerability of communities, which is an index which takes into account how much people's take-home pay versus their health index is, versus soil erosion, obviously a concern, particularly for our Midwest farmers. And then things like PFAS, these forever chemicals that we know are in many, many products that we use. Would those go up? Would they go down? Would our water quality or our air quality improve or decline if we implemented some of these carbon dioxide removal approaches? And those are the things that Kim's team analyzed. I'll just tell you in a nutshell, Indiana is in the top 3% in the entire country of states with the ability to benefit from carbon dioxide removal when we looked at all of those different indices together. In summary, I want to just tell you again that there are many different types of opportunities to remove carbon dioxide from the air. It's not the same answer in each county. It's not the same answer in each state. Indiana's opportunities are largely in soil carbon, in forest regrowth, but also in that BiCRS approach, the taking of the biomass that is currently just allowed to decay or may even be trucked to a landfill, collecting it at a different kind of facility where we make useful products, but also remove the CO2 from the stream. And I'll just tell you one more time, if it didn't come across clearly in my video, later is too late. Particularly in this state, you have opportunities that start today in terms of changing the way that agriculture is practiced, making sure, excuse me, I'm losing my voice here, making sure that our farmers are getting paid for these practices, but also benefiting the soils by increasing water hold capacity, increasing the microbial diversity of soils, which allows them to capture that carbon. I want to give thanks one more time to my team, many of them who are here, and also to the Livermore Lab Foundation who organized this event, and several who donated to allow us to come out again and meet you directly and really hear back from you how you take away the messages from this report. Thank you. I'd be happy to take questions, yeah. And I'd be happy to take a water. Thank you. You're very kind. Appreciate it.
Any questions? Yep.
Someone in the back there.
Hi, my name's Cassandra Key. I'm a PhD student at Indiana University Bloomington. We are doing a project looking at cover crops and their role in carbon, energy, and water cycles. And earlier you mentioned you have expertise in the carbon storage of plants. And I was just wondering very quickly if you have any insight on how long cover crops need to be in the soil to actually store that carbon long term or not. Thank you.
Oh gosh, I wish I could tell you a specific number of days, but the reality is it depends so much on the climate and the soils of a particular region. What we've seen overall, though, is that cover cropping is the #1 way to get soil carbon to increase in the ground. It is a big, slow-moving ship. It is easy to lose carbon and hard to gain. But the biggest way to gain soil carbon that we've seen in many, many different states across the nation is to simply keep growing plants on the surface of the soil. So when we lose 4 months out of the year by having a bare soil, not only are we leaving that soil open to wind and water erosion, but we just don't have the slow drip. It's almost like having your tap on where you don't want your pipes to freeze. You just leave it on that slow drip. And those plants that are pumping their roots and those root exudate compounds into the soil, making microbes happy, that whole community of organisms are what's causing the accumulation to happen. And I would say keep the green layer on the soil as much of the year as you possibly can. But I don't have a specific number of days. It's just anything is better than none. Yeah.
Hi. Thank you. Hello. Regarding your nerdy slide, one of the lower ones said silviculture and forestry.
Yes.
So do you have that on there like as opposed to clear cutting, or what did the silviculture represent?
So the answer there, again, I'm going to sound like a broken record here, is very dependent on where you are in the country. If you are in New England, the forests there, as they are here to the extent you have them in Indiana, are aggrading because we had a period 120 years ago where we cut them all down. So they're still growing back. They're actually accumulating carbon naturally. But a lot of our forests that are in that situation are more susceptible to some of these disease outbreaks that we've been seeing, and even some of the climate effects. Certainly in the western US, we have these forests that have been growing like gangbusters for 100 years, but too much. They're too close together. The trees are literally touching and should have at least 5 to 10 meters apart. So by thinning forests like that, you actually make them less susceptible to disease or fire. So it's a little counterintuitive by taking trees out of a forest, by managing the forest, not clear cutting, managing, you actually make it healthier and able to accumulate more carbon in the long term. There are places where, particularly in the southeastern US I mentioned, trees grow like corn, except with a 20-year rotation instead of a 1-year rotation. And in those situations, we are looking at clear cutting because we're thinking about growing trees as a crop. And it's important to think about managing nitrogen and carbon and the other nutrient resources in those soils. If you do that year on year on year and don't give anything back, the system will not continue to perform. But there are a number of systems in the southeastern US where you can grow biomass in trees as opposed to in a miscanthus or a switchgrass. So it's another opportunity to make a biomass precursor that we might use for a fuel or other product. Yeah.
We have time for 2 more questions. We'll do this one and then Carrie.
Thank you. I was thinking, besides the different agricultural practices, for example, the cover crops impact to remove the carbon, right? How about, are there also impact the crop yield that we have to thinking about it?
So I'm going to defer to my colleague Allegra Mayer, who can probably tell you more. She's wearing a bright green shirt over here, and you can ask her later on about crop yield. Again, I think it's very location specific. Cover crops were traditionally planted because they fix nitrogen. Often, if you have a clover or some of the rye, and that's a real benefit in the long run for your subsequent, your cash crop. Whether you get a yield benefit in the cash crop depends on many, many other factors. And it has to do with how much fertilizer you are or aren't using, what the climate is like that year. And so I wouldn't say that cover cropping is going to year on year improve your yields. And the cover crop itself is, in most cases, not something you're getting a cash benefit from, though I will say there's a crop called camelina where they're actually using it as an oil precursor feedstock. So the benefit really comes to the soil carbon. It comes to the overall resilience of your crop that you're growing as a cash crop, because putting that carbon, that organic matter in the soil helps you maintain a better water balance and better nutrient stores. Whether you're going to necessarily see a bump in your yield the subsequent year, I think it's pretty unlikely that you'll always see that. But statistically, year on year, we see healthier soils and benefits to the whole system. Yeah. Hi.
Jennifer, thank you for the great presentation. I'm really looking forward to teasing the details out over the next day and a half. So Janet and you both talked about some of the economic costs. Janet said many times over, the impacts of climate change, costly versus mitigation and elimination. That's not exactly what you said, but that was the intent, I believe, generally. And then you talked about 5% of GDP from air emissions and the fall-on costs from that.
Yeah.
And then, of course, there's several other buckets, right? There are all these buckets of economic costs. Is there a home for that data? Is there someone owning that so that we,
oh my goodness,
policymakers, can have a really comprehensive economic look at this?
Gosh, I can't think of a single place, though I feel like the EPA's got a lot of that data. I'm going to look at Kim and ask, can you think of a single place that you would go to for economic costs of climate change?
I'd probably go EPA.
Yeah, but not necessarily all on a single webpage. It's kind of, spread out in different places. We certainly have our costs all in one place in our data, but this is, again, just one piece of the puzzle. It's making me think we need to write another report. No, that's terrible. But I think that engaging with those costs is a critical part of all of our jobs, and helping people understand those, because it's a commons, right? Our atmosphere is a global commons. And if we don't think about the cost in terms of somebody's asthma or somebody's water quality relating back to climate change, but also relating to something that we could fix, then it's hard to get the public support that we know we need. I really like where you're going with that. Thank you. Well, thanks everyone. Again, we're all here and happy to talk more during both the panels and the breaks. So thank you again.